Maracas Beach in Trinidad has the most relaxing vibe. There are always some people lounging on the beach, enjoying a good bacon shark, and some people playing in the water. But what if all of a sudden a maxi, what we call a bus, pulls up and drops off a whole crowd of people? They will crowd the beach and disturb the equilibrium. But watch what often happens next. People naturally adjust. Some jump into the water, while others find a quieter spot on the beach. Balance is restored. Chemistry works the same way. When equilibrium is disturbed, a reaction shifts to counter the stress and bring things back into balance. This is real chem. One of the most exciting things about science is how it gives us powerful ways to reason qualitatively, to spot patterns and predict outcomes without crunching numbers. Some ideas, once they become part of your intuition, unlock whole new ways of thinking. Le Chatelier's principle is one of those ideas. It lets us predict how a system will respond to change just by recognizing the stress and how the system will shift to counter it and restore balance. Once you get it, you'll start seeing it everywhere. Imagine 100 people arriving at the beach early in the morning. Each person faces a simple choice: relax on the beach or go into the water. People will often move back and forth between these two choices. But by mid-morning, when the sun is up, we've reached dynamic equilibrium. There are consistently 60 people in the water and 40 on the beach. Remember, we can track this balance using the reaction quotient Q, as it represents the ratio of products to reactants. In our beach scene, Q represents the ratio of people in the water to those on the beach. When everyone is on the beach, Q is 0. When everyone is in the water, Q is infinitely large. At the start of the day, Q was 0, but by mid-morning, equilibrium was reached with a Q of 60 over 40, or to simplify this, 3 over 2. Now imagine a maxi pulls up and drops off 25 new people. We will now have 65 people on the beach, along with 60 in the water. The beach becomes crowded. We have introduced a stress. Let's update our Q versus K scale. Our total number of people will now be 125. Just like before, on the far left, Q equals 0, where everyone is on the beach, and on the far right, Q equals infinity, where everyone is in the water. After the maxi arrived, Q became 60 over 65. Here's the key idea. K hasn't changed. The equilibrium ratio is still 3 over 2. The system is naturally going to adjust until we return to this ratio. To get there, more people need to move into the water. This means the reaction shifts to the right. The system responds to the stress or counters the stress by shifting to the right to reach the new equilibrium. More people move from the beach back into the water. When equilibrium is achieved, we will have 75 people in the water and 50 on the beach. At this ratio, 75 over 50, or 3 over 2, Q equals K again. There's a simple way to predict which direction a system will shift after a stress. The arrival of our maxi increased the number of people on the beach, so the system shifted in a direction that countered that stress, meaning the reaction shifted to the right. This is an example of Le Chatelier's principle at work. The shift is always in a direction that counters the stress. Le Chatelier's principle gives us a powerful way to think about equilibrium. When a system is stressed, it shifts to counter that stress, always working to restore balance. This simple idea can help us reason through an incredible range of chemical reactions. But beyond chemistry, it's a way of thinking, one that makes it easier to see how the system responds to changes, whether in science, a day at the beach, or everyday life.